Hey everyone, today we're going to be employing perturbation theory to solve for the real solutions to x to the third equals 1000.001 plus 1 over x, accurate to at least plus or minus 10 to the negative 8. So to do this, we're going to employ this hint. How might this number be expressed purely in terms of a small parameter epsilon? Well, setting this up, we can make epsilon equal 1 over 10, purely for, I would say, cosmetic reasons. But the goal is to turn this problem dimensionless so that we can work with all variables instead of numbers. And then we can manipulate these easier later on. The reason why it's set to 1 over 10, the quote-unquote cosmetic reasons, is because 1000.001 is very symmetrically broken up into a 1000, which is 10 to the third, and 001, which is 10 to the negative third. The reason why this is set to 1 over 10 instead of 10 is going to be because this is a small term. So think of this kind of like a expansion term. So every single subsequent series you want to make it smaller. And the next thing after getting this equation you're going to be doing is just these general steps. This is recommended to solve a lot of these perturbation problems. So instead of trying to factor out every single polynomial instantly using, let's say, series expansion, because this is an unrealistic amount of work, especially if you want to get to like very small terms. Instead of doing that, what we could do is guess which terms are dominant, and then solve for those instead. And then after that, expand around the dominant terms. So this is just a good rule of thumb. Maybe we could set these epsilon, break them into p equals 0, p greater than 0, and p less than 0 as just rough estimates of maybe where the solutions are. And over here, just a refresher on the equation, it's x to the 4 minus x to the 3, right? So to the 4 means that this is going to be a quartic solution, and meaning there are there are going to be 4 answers. However, 2 of them are going to be imaginary. All right, so if 2 of them are imaginary, then 2 of them are real. So over here, we're going to try using p equals 0 for now. But we're going to see that if we use p equals 0, if we set x on the order of p equals 0, then what is that? That's x is on the order of 1, right? So let's see if there's any actual solutions to this. Well, let's see. So we have 1 over here. We have x on the order of 1, so e is going to be really small. This one e is going to be really large. And then over here, we're going to have like 1 to the 4. And at the end, you're going to have something like, what, 1 minus 1 equals 0. There's not going to be really anything on the scale to compare, because each of these terms, the largest term is going to be way larger than anything. So none of these terms will really cancel out. So there's no roots where p equals 0. Now we want to set x or p greater than 0. So if p is greater than 0, then that means epsilon is going to be very small, or x is going to be very small. Because if x is on the order of e to the p, then it's going to be at least 1 over 10. So we know that if x to the something power, like a high power, is going to be really small because it's already set to small. So we can take out x to the 4. And then x times e to the third, we know that's going to be like what, 1 over 1000 times, again, 1 over 10 at least. Then that's also going to be really small. So the only ones left that are going to be a reasonable size is going to be x e to the negative third and negative 1. So let's guess that these two are the dominant terms. this is still a guess. We're not too sure yet, but we'll be checking these later. So guessing these two are the dominant terms, we just solve for these, and we'll get something like x is going to be negative e to the third, which means that p equals 3. So let's check if this is true by plugging p equals 3 into all of these terms. Well, you're going to see that x to the 4 equals e to the 12, which is really small, of course. X e to the negative 3 is going to be e to the 0, which is on the order of 1, or order unity. X e to the 3 equals x e to the 6, which is really small, and then 1 equals e to the 0, which is, of course, 1 again. So, okay, that means our assumption is true, and that we can now expand x around our solution of 0.001. Let's just expand 3 terms, because we know that after expanding 3 terms, with all these multiplications and stuff, you're gonna be getting at least somewhere to x to the 8 or x to the 9 without having to do too much work. So let's expand this. You expand this, you're gonna get this really big number. And after that, usually what you would do is you take all of the epsilon and then group all of the values with the same e next to each other. As seen here. And eventually you're going to get a lot of zeros. So any term that's by itself basically is on its own order of magnitude, right? So you basically can cancel everything or pretend that they don't exist because they don't influence each other. Then you see that they're set to 0, and that's how you get the 0. However, the only one left is going to be the e to the 6, and that one is going to be negative x plus 1. So that one, negative x9 plus 1. So that means that x9 is going to be 1. And if x9 is 1, well, what's x9? x9 is going to be e to the 9th. So now we can solve for this solution where x is approximately negative e to the third plus e to the 9th, which is definitely plus or within the plus or minus range of this solution. Okay, cool. So we got one root. Now we want to find the other real root. So now p is less than 0 is our last assumption. So okay, in the range that p is less than 0, x is going to be around e to the p, where e is going to be 1 over 10. So that means if 1 over 10 to the power of something that's negative, that means it's going to be large. So then the two values that are going to be larger than any others, most likely, are going to be x to the 4 minus x to the e to the negative 3. And let's just check this again. So balanced terms, you're going to get p equals negative 1. And plugging in p equals negative 1, you're going to get everything is going to be, or x is going to be on the order of 10. So yeah, that's true that x is going to be larger than this value. So now we can work with this. You expand this around 10, but then the scale, of course, always decreases every time. And plug this into the equation for x, the expansion into x. And after this, you'll be getting a similar set of equations, and you're going to see that x to the 4, or x4 equals x6 equals x8 equals 0. So all of these are going to be set to 0. However, x3 equals x5 equals negative 1/3, and negative x9 equals negative 1/3, so x9 equals 1/3, and x7 equals negative 2/9. And after that, okay, let's see. So we have all these, then we can add them all together and get x is roughly 10.000336664. And how many powers is that? 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. So we got 10 to the plus or minus 10 to the 8. So great, we got our two roots, and the other two roots are complex, so we won't be solving for those since the original question just asked for real roots. But I hope this helps you solve for the real roots.